That was a joke. Hi, everybody. Welcome back. We are doing work, circulation, and flux. And flow is just a subsection of circulation. So we did work last time. Today's lecture will conclude this subsection. I think it's 16.2. And then we'll move on to 16.3. I encourage you to read all of the remaining part of 16. Even if you don't understand what's going on, okay? Just read ahead, everybody, because it's going to come like a train at the end, and always does in this class, okay? Stokes' theorem comes like a bit of a train. So today I want to talk about, let's start talking about flow. So work was defined over vector fields arbitrarily in R3, R2, wherever you want them. But circulation and well, flow and circulation tend to be defined over R2 or R3, okay? But we're going to do everything pretty much over R2. Flux, this is the important thing. So flow and circulation, like work, circulation, similar to work, makes sense in R2 or R3, okay? However, the flux we're going to define today, the flux we will define today is exclusive. Hello, I'm back. There we go. Exclusively for R2. Okay? There will be an R3 version of flux, but that comes later. We have to do the R3 version of flux later. Okay? And when we define it, maybe it'll make sense to you why. That this one, well, I will clarify why. So let me just say what they are first, okay? Flow. The flow of a vector field over a curve is equal to the line integral over the curve of the vector field dotted into the tangential component ds. This looks a lot like work, right? If the vector field was a force field, this would truly be work, okay? But really what flow is used to calculate is when the vector field is a velocity field. So flow is for F when F is velocity in meters per second, or, okay, this is the other thing, or when it is in momentum density. And what momentum density is when the vector field F is equal to like a density times a velocity vector field, where delta is a density, okay? It's like a mass density. So you think about this for something like water, where this is like kilograms per cubic meter, or grams per cubic centimeter. I know water in grams per cubic centimeter, right? The density of water in grams per cubic centimeter is 1. That's nice. Thank you to the Napoleonic system. Kilograms per cubic meter, though, and meters per second. So this would be kilograms per square meter per second integrated over a curve. So the units of this are kind of a little bit odd, okay? A little bit odd. But the act of actually computing this, I'm actually not even going to go through it. Because what is this? What did I say? Well, this is exactly like you would do to compute work. So it doesn't need much more commentary, right? In order to compute the flow, what you do is parameterize the curve, so you go from some t0 to t1, and you evaluate the function f of r of t, and then the tangent vector, of course, depends on r of t, where you are along the curve, and then ds is really ds dt, which is the magnitude of dr dt, integrated with respect to time. And of course, this combination is simply f of r of t. This times this is simply dr dt, dt. So as I said last time, you really want to parameterize the curve and compute it this way. This will work every time. OK? That's flow. That's it. I'm not going to bother computing it because I'm going to compute an example of it when we do circulation. What's circulation? Circulation is equal to the flow if the curve is closed. That's it. Yes, ma'am. T hat is the tangent vector along the curve. So it is a function of t, the parameter. But what this means is it depends on where you are. And this means where you are depends on when you're there. OK? I'll do an explicit example in a moment, right? But you see that this combination is just dr dt. That's what we mean by it. Okay, so computationally, it's pretty straightforward. Circulation is literally the flow if the curve is closed. Yes, sir?
Does it matter if the closed curve is simple or not?
Yes, totally. Okay. So closed, and let's make it simple. And simple means non-intersecting, non-self-intersecting. And it also means non-detached. And non-detached. But the important part is non-self-intersecting. Let me show you why in a second. So notationally, all we write is that the circulation is the integral, formally, this is integral around the curve C, like that, of f dot t hat ds, where I've introduced this little circle. And we just do that as a shorthand to remind ourselves that this is closed. It's supposed to be a closed circle, so I should keep it closed. So we use this for closed circles. And the reason is that these kinds of closed curves come up in a lot of functional analysis as we go forward. And so this is an important kind of integral to go forward and do. So I point people to complex variables classes where such integrals will come up a lot. Circulation is important. I'm going to just tell you why circulation is important. For a perfect fluid is a fluid with no viscosity, so an idealized fluid, studied by Lord Kelvin in the 1850s. There is a theorem called Kelvin's circulation theorem. And Lord Kelvin proved that if you take a loop of fluid, just any old curve in the fluid, and move with that curve gets moved around by the fluid. Okay? So that curve gets moved around by the fluid. If you calculate the circulation around that curve at some fixed time, some initial time, and then calculate the circulation around that curve at any other time, it will be the same. So the circulation is actually conserved. So this is called Kelvin's circulation theorem. Now, you do not need, for this class, to know Kelvin's circulation theorem. You have no need. I am not going to test you on Kelvin's circulation theorem. We can't even discuss fluid moving things around because I haven't talked to you about the equations that govern a fluid. Kelvin knew them, however, and you may need to know them especially if you're in anything like aerospace engineering or any time taking fluid dynamics or anything like that. Okay, aerodynamics, anything like that. This is an important theorem, and it's totally related to conservation of angular momentum. Okay. And so that motivates the reason why we would bother introducing this apparently very specific concept in a fluids class. and sorry, in a calculus class and not in a fluids class. We do it in a calculus class because it's ubiquitous in fluids. But it has to do with something that's very fundamental in all of physics, which is angular momentum conservation. Okay? So that's where this comes out. Now, I'm going to actually just compute a couple of these, if you don't mind. Okay? So let's compute a couple of these things. And I want to make reference to my basic vector fields again. Okay? So I am going to compute circulation. If I can compute circulation, I can compute flux. Sorry, flux. Flow. Because flow is just circulation over an open curve. Okay? So let's do circulation, e.g. circulation over a curve C. And I'm going to use two different curves. Okay? We're going to do two different curves, C1 and C2. And C1 is going to be circle of radius A centered on origin. And C2 is going to be square of side length 2A centered on origin. Okay? So we're going to consider two different curves, this curve right here and this curve right here. And if you take a look at the definition of flow, coming back over there, the definition of flow, you notice that it's the dot product of a vector field with a tangent to the curve. So something about the flow and the circulation must have something to do with the direction that you go around this curve in, right? So if you go around counterclockwise, and we have a sense of counterclockwise, you should get one number for this integral. If you did the same curve clockwise, you should get exactly the same number, but with a negative sign, right? Because the dot product is opposite. Okay? So it depends on direction. So circular flow and circ depend on direction. And you can see that I'm going to just go with we're going to go with counterclockwise because the circles, we know the counterclockwise parametrization for the circle like that. Okay? And so you might as well stick with it for these other examples. Okay. I want to make a comment about the closed curve, the simple closed curve issue. Okay? Let me make the comment about the simple closed curve issue. Because now that we talked about clockwise and counterclockwise, I can talk about a simple closed curve. Okay? And this is going to come up when we do flux in a second. So imagine a curve. I'm going this way. Okay? And let's continue going through, and we're going to make like a figure 8. Okay? So what's the issue with a non-simple closed curve? Well, the change in the tangent vector here is extremely important. So as I drew it continuously, so it came around here and came back. Right? We draw the 8 like we learned how to do it in elementary school or nursery school, right? We draw it this way. But if you think about this curve, and you were to think about it in two pieces, if you were to think about it in two pieces and imagine joining those two pieces right here, counterclockwise is this way, and counterclockwise is in the opposite direction. So we execute this loop in a counterclockwise sense, but then, strangely, in this loop in a clockwise sense because of self-intersection. Okay? And why is that going to be important? Because in a moment, we are going to define what is called the outward normal. Okay? And we have to find a way to consistently define the outward normal. Okay? And we define it with tangent vectors. So if this is the tangent vector, okay, I'm going to define my outward normal like this. Well, that is the outward normal, okay? But I have up going this way, okay? And what you see is t hat cross up is out in this direction. And that's consistent, right? But if I were to have my tangent vector over here going this way, t hat, and up is going this way, t hat cross up is now in. Okay? So this is in, and this is n hat out. And this is n hat in. I will do more of this in detail in a second. And this has to do with the fact that locally here, around this part of the curve, we are actually going clockwise. Okay? So we avoid these situations because we want to say, okay, look, I can whatever I want to do, whatever integrals I want to perform over this curve, I'm going to perform over this curve alone, and then I'll perform over this curve alone. So we separate the two curves. That's the best way to deal with these kinds of problems. Okay? But right now, I haven't defined for you the normal vectors just yet, and I'll get to that when I get into the flux part of the calculation. I hear a little bird chirping. Okay. I'm going to erase this staying on the same side of the room, and I want to calculate flow and circulation around those two curves for two different vector fields. And I'm going to just use two very straightforward vector fields, my two basic vector fields that I got last time. Okay? So vector field 1, or vector field A, is going to be F equals omega, some parameter, times negative y I hat plus x j hat. Okay? And that's, remember, this was the circulating vector field. This is the one that went around and around. The vortex. And then F equals alpha x I hat plus y j hat. This is the one that was pointing radially outward. That's the one that's pointing radially outward. Okay? I have to calculate on both of those vector fields. Okay? So let's first calculate the circulation over the circle of radius A for both of these. Well, the circle of radius A is very straightforward because we know the circle of radius A, we're going to do curve 1. Curve 1 is given by r of t is equal to a times the cosine of t I hat plus the sine of t j hat. That's how we parameterize the circle of radius A executed in a counterclockwise direction. So you should always say where your limits of the circle are. So it goes from 0 is less than or equal to t, which is less than 2 pi. And that gets you once around the circle. Okay? So I might as well just evaluate both of those vector fields on the circle of radius A. So for part A, f of r of t says, hey, just evaluate that vector field at x equals x of t and y equals y of t. Well, that's going to be omega times y, sorry, negative y, that's the circulation vector field. It's negative y is going to be negative a sine t I hat, because I'm putting the y in the I hat position. This is negative y. And remember, y is the y component of r of t, plus a times the cosine of t j hat. That's f of r of t for part A. So all I'm doing is evaluating that vector field on the curve. And for part B, f of r of t, for the second vector field, well, that's alpha, and I have x I hat, which is a cos t I hat, plus a sine t j hat. So this is x I hat plus y j hat, which is the second vector field. And I'm sorry I split boards. I came across the room for those of you guys watching at home. Sorry. OK. What else do I need? Well, in order to compute the flow or the circulation, I need to calculate dr dt. And that's the same, because it's the same curve. It's the same for either case A or case B. So we write dr dt is simply the time derivative of this thing, which is going to give me a times negative sine t I hat plus cos t j hat. And now we're primed to do the integration. So the circulation in part A, again I'm doing part A, which is the rotating vector field, is equal to the integral, and always write this out, the integral around the closed curve C1, and I'm dealing with C1, of f dot t hat ds. That's the formal definition. And that's going to be the integral from t equals 0 to t equals 2 pi of f of r of t times dr dt, the dot product of dr dt, integrated with respect to time. And I pre-processed all of this. It's already been processed, so I can just do the dot product. And since I'm running out of board space here and I'd like to stay here, I'm going to erase the previous line and just continue as though I'm looping over the board, OK? But I write very big, I guess. So what's this equal to? Well, this is equal to, coming up back to the top, the dot product of f of r of t with dr dt. So that's the line A above me with this. Well, notice there's an omega in front associated with the vector field. There's an A that I can factor out that's also associated with the vector field. There's another A which is associated with the dr dt. And then I just have to take the dot product of negative sine t I hat plus cos t j hat with negative sine t I hat plus cos t j hat. And what you see is that this curve that I've chosen is everywhere tangent to the vector field. Or the vector field is everywhere tangent to the curve. And so sine t times sine t is sine squared, plus cos squared is 1. So this is going to be sine, I'll write it out, sine squared t plus cos squared t. The integral from 0 to 2 pi dt. Which is equal to, well, this is 1 integrated with respect to t from 0 to 2 pi is simply 2 times omega times pi a squared. And I'm going to write it like that. Why did I write it like that? Well, the pi, I got a 2 from this. I got a pi a squared. This looks like an area. And the omega is this frequency associated with the vector field. Okay, that's, I think, a little interesting. So the circulation for part A is 2 pi omega a squared. Let's look at part B now. And part B is, I hope you get an intuition for this right off the bat. I don't have to work too hard to get part B. Okay? Because notice that for part B, it's the same curve, same circle. Part B, the circulation is equal to the integral from 0 to 2 pi times f of part B of r of t dot dr dt integrated with respect to time. But again, I'll get an alpha up front, an A from the vector field, so there's alpha A, an A again from the dr dt, and then I have to take the dot product of those two vector fields, and I'm going to write it out. I have cos t I hat plus sine t j hat. That's associated with f vector. This is radially pointing outward along the curve, dotted into negative sine t I hat plus cos t j hat integrated along the curve. And I don't have to do another ounce of work here, because this is tangent to the circle. This is perpendicular to the circle. Therefore, they're perpendicular to one another. Therefore, at every point along the curve, these are 0. Therefore, the integral of 0 is 0, and this thing is 0. So the circulation of the rotating vector field is something, and I've factored it in a particular way. The circulation of the expanding vector field is nothing. Okay? I also want to point out to you, if omega was positive, circulation would be positive. If omega was negative, circulation would be negative. So circulation has to do with the sign of the rotation, as is evidenced by that formula right there. So this is everything along the very straightforward, simple curve, which is a circle. Okay? What about along the square? So I should do this now along the square. Okay, I have to parameterize the square, right? It's going to take a bit. You guys bear with me? So, square. The square, I'm going to parameterize as 4 lines. It's going to be 4 lines, right? 4 straight lines. Okay. I'm going to call C2 is going to be equal to, that's just the square, it's going to be equal to line 1 plus line 2 plus line 3 plus line 4. You okay with that? Line 1 plus line 2 plus line 3 plus line 4. Okay? So what's line 1? Line 1 is going to be, let me draw it out. Let's call this one line 1, line 2, line 3, line 4, line 4. Okay? And we're going counterclockwise around this square. Okay? What's this point? Well, this point is positive A, comma, negative A. And this point is positive A, comma, A. So line 1 is actually pretty easy to parameterize, right? Line 1 is given by R of t equals, well, the x component is constant. It's AI hat plus, just parameterizes it as tj hat, where negative a less than or equal to t, which is less than or equal to a. That's a super simple parameterization. And of course, I can go to line 2, which is R of t. You do the same thing over here. Okay? You got to be a little careful. Let's just be very careful here. R of t is equal to, well, it's going to be aj hat. Right? And I'm going to have ti hat plus aj hat, where now t goes from, I want to keep this so t increases in time. So let me make this so t increases in time. I don't want to do it that way. Let's make t go from a negative number to a positive number. And if you do that, life works out better. You don't make sign errors, okay? So I have to have t go from a negative number to a positive number. So I'm going to have negative t over here, and t goes from negative a less than or equal to t, which is less than or equal to a. Okay? That makes it easier. Makes it less likely that I'll make a sign error, because I've been known to make sign errors. Line 3, somebody want to shout it out for me? So line 3 is the one on the left. So it's going to be R of t equals negative a I hat minus t j hat, where again, t is less than or equal to a is greater than or equal to negative a. So it's always going positive again, right? And finally, line 4 is going to be given by r of t equals ti hat minus a j hat with the same bounds of integration. Okay. So now this forms a closed curve. So the circulation is equal to the integral over each of these. So line 1 plus of all that stuff, I'm going to write just dot, 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 dt, plus the integral over line 2, dot, 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 dt, plus the integral over line 3, dot, 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 dt, plus the integral over line 4, dot, 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 dt. Okay? Okay. So by the way, I hope that when I do this, it's a little tedious, isn't it? We're going to learn that there's another way to calculate this integral using Green's theorem. Okay? That's one of the reasons we learn Green's theorem. And Green's theorem will make this calculation ridiculously simpler. Okay? So all this parameterization goes away, which is why we learn Green's theorem. So you see my sweating here. Do I do this? Do I not do this? I think I got to bite the bullet and do this for you. Okay? You happy that I do this for you? You guys look so excited that I'm doing it for you. No, we just have to do it. So let's just do this for each of these parts. Let's take a look. Let's look at, so I'm calculating essentially 8 integrals. I got to do all these 8 integrals. There's 4 for the first vector field and then 4 for the other vector field. So we have to do them for both vector fields, right? Because I got 2 vector fields. I got the rotating one and the one that's expanding out, okay? The radially expanding one. So let's calculate this integration. Let's do this integration right now. The integral over line 1, so the first one, okay, so again, part A. Part A has the vector field f is equal to negative omega y I hat plus x j hat. Okay, that's the vector field I want to integrate around. So the integral over line 1 of the flow that I have to do over line 1 is the integral from negative a to a of f of r of t along line 1. So I have to evaluate f along line 1. And the point is, along line 1, y is equal to t, and x is equal to a. So f of r of t is negative omega. Y is equal to t I hat, and x is equal to a j hat. And by the way, I put the negative in the wrong place, everybody. This is omega times negative y. So there's a negative t. It's inside the parentheses. I apologize. Multiplied by dr dt, but dr dt is super easy over here. Dr dt is j hat. Right? Dr dt is just j hat. And then I have to integrate this with respect to t. Oh, all of a sudden we see a simplification. Because dr dt, the way I've chosen this parameterization, it's a line. It's going to be a constant, right? So you take a look at this, and you've got a times omega. J hat dot j hat is 1. J hat dot I hat is 0. So all you get is a times omega, and it's constant. And then you're integrating from negative a to a. So this is going to be 2a squared times omega. Okay? Do you see that? This is a j hat, j hat. Now, here's a terrible argument. You can all throttle me for this argument. By symmetry, right? I just did the integral going up, and this whole thing is rotating counterclockwise, right? Well, if I were to do the integral here and it's rotating counterclockwise, it should give you the same amount. If I do the integral here and it's rotating counterclockwise, it should give you the same amount. In other words, each of these 3 other integrals are going to give you the same number. You see it? I mean, just like think of the geometry, right? They're all pointing, all the vectors are, these guys were all pointing like around this way, and I'm integrating this way. So by symmetry, each of those gives you the same number. Therefore, by symmetry, the circulation is equal to 4 times this. Okay? And if you don't mind me writing 4 times this, I'm going to write 2 omega times 4a squared. There's one from each of those 4 integrals, one from each of the sides of the square. And what you see is the circulation, in this case, comes out as the area of the square times 2 omega. And in the previous case, it was the area of the circle times 2 omega. There's something, this is alluding to Green's theorem right here. There's something about area, which is related to area integrals. And then this weird constant, which is associated with the vector field. Okay, twice the constant, actually. That's associated with the vector field. That this will be all clarified when we do Green's theorem. But this is not a coincidence. This is not a coincidence. Okay? That's the circulation around this vector field. Okay? Circulation around this curve of this vector field. Well, yes, we have a question.
I have a question about the units. So what exactly would the units be units? Like, if A would be like meters squared, but is omega just, like, what is the units of omega?
Omega, so if you go back, let's go back. It's a very good question about units. Let's return to our original vector field. This is in units of meters. I wanted F to be a velocity. Omega is like a frequency, so it's inverse time. It's like in hertz. So this is meters per second. Now, you've asked a great question. What is the unit of omega times a squared? Well, it's meters times meters per second. That's an angular velocity. That's an angular velocity. Remember I talked about conservation of angular momentum? It has to do with the angular velocity of this thing. It has to do with the amount it's rotating. Okay, so the way the thing that I tell students is think about a fisherman putting out a circular fishing net, okay? And it's in a flow. Okay, this is related to the angular velocity of that net in the flow. Okay? But that's that curve associated with Kelvin's circulation theorem. Okay? Okay. This was the circulation of the rotating vector field. Now, what do you think the circulation is of the one that's expanding? Well, it was 0 before over that curve. Maybe it's still 0 over this curve, right? So let's see that it's 0. Let's see if it's going to work out to be 0. So I need the same 4 curves, right? I need to do the same 4 integrals. But if we're lucky, things might cancel. Okay? So let's take a look at it. Now part B uses the vector field. So part B uses the vector field F is equal to alpha. This is a reciprocal time also. Okay? xi hat plus yj hat. Okay? xi hat plus yj hat. Now let's consider the integral over line 1 of all of that stuff dt. Okay? Let's consider the integral over line 1 of all that stuff dt like I did before. Well, that's the integral from t equals negative a to a of f of r of t. So I have an alpha. And again, x of t, I'm going over line 1, which is way back there. X of t is just a constant. It's a. And then I have this I hat. But y of t is tj hat. So y of t is t. And so I have to multiply that by j hat. So I have tj hat. And then dr dt on this curve, again, is j hat. You see that? And you have to integrate this with respect to t. Again, you have that j hat dot j hat issue, so you only care about this one right here. And so this thing becomes alpha times t integrated from negative a to a, integrated with respect to t. And that's 0, because this is the integral of an antisymmetric function over a symmetric domain. And so this is 0. Or you can just show this as t squared evaluate the upper, t squared over 2 evaluate the upper bound minus t squared over 2 evaluate the lower bound. They cancel out. It's 0. Over the integral over line 1 is 0. The integral over line 2 is 0. 3, 4 is 0. The circulation around this curve is also 0. Because the circulation has something to do with this vector field, not only the curve. It's the we're going to learn something about this vector field circulation. Okay? And so that's how you go about computing circulations. And flow is just if you didn't have a closed curve. Okay? Now, where is my eraser? There's the eraser. I'm running out of time, but I'm going to state the definition. And I wish I had a little, I'll probably have to keep doing this on Monday. I want to talk about flux. Okay? Flux, like I said, this flux that we're talking about right here is truly a flux in 2 dimensions because it's going to be a line integral. The flux is always defined around a closed curve C, and it is f dot little n hat ds, where little n hat is the outward normal. I am going to spend more time on this. I'm going to do computations with this on Monday, so I'm not going to be done with this today because I want to spend some time talking about this. Okay? I want to tell you right now that flux, I'm going to define flux in 3D. We're not there yet, but I'm going to define it. Okay? In 3D, the flux is equal to the double integral over a closed surface. You guys are strong now, strong with the calculus. Right? So I write something like this and you're like, I know what he means. Okay? Times the vector field of the vector field dotted into the normal to the surface, the perpendicular to the surface, integrated with respect to the surface area. That's a sigma for surface area. Okay? This is the 3-dimensional version. We don't know how to compute these integrals yet. I think that's the topic of 16.6, 16.5, 16.6. We're going to learn how to compute surface integrals over arbitrarily curvy surfaces in R3. It'll be lots of fun. It is. It's totally fun. But the reason I'm saying flux in this sense is only limited to 2 dimensions is that you need to have a closed surface. You need to have a closed curve because you need to bound a domain. You have to encompass stuff. You have to have a closed domain. Okay? You're integrating around a closed domain. In 3 dimensions, to integrate around a closed domain, you can't do that with a curve. You can't close in stuff with a curve. You just get out of it, right? You need a surface, like a balloon or a bubble. Somebody reminds me I will bring bubbles to class for the last day of class because it's related to Stokes' theorem, okay? So we'll do bubbles. So you need this surface integral when you're doing this in 3 dimensions because you need to close in a domain. Now, what is the flux? What do we mean by flux? Let me just talk about units for flux right now, okay? I haven't told you what the outward normal is. I'm going to teach you how to compute the outward normal, and I'm going to do that because it's algebra, and you guys don't have any more brain for algebra. It's almost lunch. So I'm not going to do any more algebra right now. I'll do that on Monday. Let me talk about what it is, okay? You know what an outward normal is. It's a perpendicular, right? If you are on a boundary, you know which way out is. Okay? You know which way along is. So you know n hat has to be perpendicular to the tangent vector. So I'm going to be using this perpendicularity to I know how to construct tangent vectors if I have the curve. I'll show you quickly. It's really easy peasy how to construct n hat normals. Okay? So there's a normal vector at every point along the curve. Which way is the fastest way out? Okay? On top of that, so that's a property of the curve. And you can see that we need to use the tangents to construct it. On top of that, there is a vector field everywhere in space. I wish I had a different color, but here you go. This is the vector field F. Okay? I think the best way to think about this is with momentum density. Let me talk about momentum density. What is momentum density? Momentum density is the following. Well, we know what momentum is, right? Momentum is mass times velocity. Okay? Mass times velocity is momentum. Momentum density is mass per unit measure of the space, whatever the measure of the space is. Okay? In 2 dimensions, your densities are surface densities, mass per unit area. Does that make sense? So this is mass per unit area times velocity, and this is what we mean by momentum density. And you can see that in 3 dimensions, this would be mass per unit volume. But the number we'll calculate will be the same whether we do this in 2 dimensions or in 3 dimensions. Okay? So now let's just do a dimensional analysis here. Okay. First, I want to point out that this integral says take the dot product of the vector field, say this is the vector field F, and this is n hat at this point. Take the dot product. If the dot product is 0, that means the vector field is tangent to the domain. If the dot product is maximal, that means the vector field is perpendicular to the domain. It's pointing out. Okay? So this measures the outness, the outward component of F. This measures how much of it is pointing out. Okay? Now let's do a unit calculation here. What did I say? I'll just leave it here. The units of F are kilograms, that's the mass, per square meter. This is density, mass per unit area is the density in 2 dimensions, multiplied by a velocity, mass per unit time, by velocity, meters per time, meters per second. Okay? The units of the normal vector, well, of course, they are nothing. They're unitless. And the units of ds, well, it's a length. It's a length integral, so that's in meters. So let's take the product. I've got kilograms, meters per second per meter squared times meters. This is from the F, the n hat has nothing, and this is from the ds. So I'm going to cancel meters and meters with the meters squared, and you have kilograms per second. Kilograms per second. And now this should tell you what flux is. It is the amount of kilograms per second of the stuff flowing out of the domain. Right? If it integrated to 0, because maybe it was flowing out at one point and flowing in at another, that means wherever it's flowing out, it's compensated for by wherever it's flowing in. So the change in the mass per unit time is 0, according to this flow. But if it has a net amount, that means it's net flowing out or net flowing in. I mean, if it's positive, it's net flowing out. If it's negative, it's net flowing in. So it's the net mass per unit time flowing out if greater than 0 and in if less than 0. Okay? That's what it is. And you can think fluxes are interesting. And one of the examples I use a lot is like, I like to think about satellite dishes and the flux of radiation hitting a satellite dish. Or a rain gauge. We're going to be thinking about rain gauges, okay? And you think about, the perpendicular, and you think about, or like a windshield, right? And rain falling. If the windshield's oriented vertically, the rain falling this way, it's missing the windshield. If it's oriented this way, it's coming through the wind, that hitting the windshield, effectively coming through, okay? Conceptually. So this is what flux is all about, okay? And it's important for electricity and magnetism, it's important for fluid dynamics, it's important for all of these, and it's important for Green's theorem. So I'll do a whole bunch of computations for you on Monday. Please read ahead, and we will be moving on to conservative vector fields also on Monday, okay? Have a good weekend.